Hi everyone, in this talk, I'm going to introduce our work, SSCAP, Self-supervised Co-occurrence Action Parsing for Unsupervised Temporal Action Segmentation. This work is done from Amazon AWS AI. I'm Hao Chen, and I will be presenting our work. Temporal action segmentation is a task to classify each frame in the video with an action label. Today's high-performing solution for temporal action segmentation require full frame-level separation. However, collecting per frame annotations in untrimmed videos is extremely expensive and often impractical. Some recent work aimed to overcome this by leveraging weak separation. However, it still relies on non-trivial expertise in annotation. We ask the question, can we do it in an unsupervised manner? In this work, we introduce SSCAP, an unsupervised solution for temporal action segmentation. SSCAP uses self-supervised learning to extract features that are more temporal distinguishable. It also builds a co-occurrence action parsing algorithm to capture the correlations among subactions and handle complex structures and the recurrences of subactions. It achieves state-of-the-art result on not only breakfast salad, but also fine-gym, which is an emerging and more challenging dataset built on fast-moving gymnastic actions and with more complex action structures. Here is an overview of our SSCAP solution. It consists of three main units: feature generation, cap clustering, and cap decoding. In the following slides, we will introduce each of them in details. The first unit is the feature generation. It is where the per frame features are extracted. In order to generate more distinguishable features for the task, we explore self-supervised learning methods. Specifically, we explore three types of self-supervised learning: SpeedNet, which augment and predict different frame rates; Shuffle Learn, which randomly shuffle the video and predict whether it's shuffled or not; and finally, RotationNet, which rotate the video and predict the degrees of the rotation. The second unit is the cap clustering. It first clusters all the frame level features into K clusters using K-means. After that, it generates three outputs: the video score matrix that captures the score of each frame belonging to a cluster, the co-occurrence matrix that captures the correlations among subactions based on the times they co-occur, and finally, the cluster temporal location histogram, which estimates when each cluster happens in a video based on the timestamp of each frame in the cluster. In the cap decoding unit, we first refine video score matrix with co-occurrence matrix to capture the correlation information among subactions and global activity structures, so as to filter out non-existing classes and avoid over-segmenting the video. Here is a snapshot of the algorithm. For details, please refer to the paper. After that, we estimate the temporal path by first selecting top K-bins from each cluster histogram, and then put them into an order. Such temporal path is able to capture the recurrence of the subactions. We decode the path with the Whitebit algorithm. Here are results of SSCAP comparing with state-of-the-art solutions. We can see that SSCAP achieves state-of-the-art on all datasets. Especially, SSCAP achieves significant improvement on fine-gym over baseline, demonstrating the effectiveness of it in handling videos with more complex structures. Then we run ablations on each design unit. Results show that all the units contribute to performance boosting. We also run ablations on self-supervised learning method. In the highlight, we find that while SpeedNet performs the best, RotationNet consistently performs worse than SpeedNet and Shuffle Learn, indicating that self-supervised from temporal augmentation is important for the action segmentation task. Finally, we show some visualization results. We can see SSCAP is able to effectively suppress the over-segmenting issue using the co-occurrence of the subactions and notably improve the segmentation quality.